When you tell the drive to decelerate a spindle, the drive automatically figures out how much reverse force to apply to get the spindle to slow down within the deceleration time. But there's a problem with that, and to understand that, you need to understand how a drive works. In the simplest terms, the drive takes a sinusoidal input, single or three-phased, rectifies it, and sends it to some large electrolytic capacitors to create a DC voltage. For example, in the drive I'm using, the DC voltage runs in the mid 300 volt range. The drive then uses some large transistors called IGBTs to turn a DC voltage on and off in a pattern whose average magnitude emulates a sinusoidal waveform. Because the power to the spindle is controlled by digital on-off pulses, the drive can very accurately control the motor speed by adjusting the frequency of the pulse waveform. For our spindle, a frequency of 400 Hz gets us 24,000 RPM. We'll use the terms frequency and speed interchangeably in this video since they both tell us how fast the spindle's rotating. Here's the problem. When the drive applies pulses to force the spindle motor to slow down, all of the inertial energy built up in the spindle has to go someplace, so it gets pushed back into the drive. If you're familiar with Regen on an electric car, yeah, that's the same thing. That Regen pushes energy back into the large capacitors, which raises the DC bus. The faster you try and decelerate the spindle, the higher the DC bus goes. If the DC bus voltage goes higher than the components in the drive can handle, well, they start to fail and your drive dies. Most drives will sense this, throw an overvoltage fault, and turn off the IGBTs. The spindle's then left to spin down on its own. The solution is simple. Add a high wattage braking resistor. The GS20 drive will automatically reroute any excess energy to that resistor, where the excess energy gets released as heat instead of raising the DC bus. On the GS20 series of drives, you just add the braking resistor to these terminals. I also added a switch so we could quickly switch the resistor in and out for our testing. How do you know what size resistor to add? Well, for the GS20 drive, it's easy. Appendix A of the user manual has a chart that says for our drive, the minimum value resistor is this, which limits the max current to this, so the max power it needs to dissipate is this. Given that, you can go to Amazon to find a resistor that'll work, or click on this guy to see all the compatible resistors Automation Direct has. Scroll down to our drive, and we see this guy is the recommended resistor. That's all there is to it. No parameters or configuration required. You just hook up a resistor. Everything else is done for you. Let's do an example. We're going to make heavy use of the GSoft2 drive configuration software in this video to change drive parameters and to monitor what's going on inside the drive. It's free, and Automation Direct has a bunch of tutorial videos showing how to use it, so I'm just going to use it here without a lot of explanation in this video. I'll put links to the free download and the videos in the description below. First, let's see what happens when we tell the drive to just let the spindle coast to a stop with no controlled deceleration from the drive. The good news is, since the drive isn't forcing the spindle to stop in a certain amount of time, there won't be any regen to deal with. I put a large surfacing bit in the chuck just to add a little more inertia to the spindle. Parameter 0.22 is the stop method. Set it to a 1 to coast to a stop. I love the way GSoft2 tells me everything I need to know about a parameter at a glance, no looking stuff up in the manuals. We see the write was successful. I'll bring up the scope function in GSoft2 and monitor the spindle speed. Start the scope, and in GSender, I'll set the spindle to 24,000 RPM and hit run. Wait for the spindle to ramp up to speed, then stop the spindle, and wait for it to ramp down. This is going to take a few seconds. While we're waiting for the spindle to stop, I'll show you that I'm using GSender on a separate screen to control the spindle using this guy down here. Okay, the spindle finally stopped. I'm going to adjust the scope display so we can see where the spindle ramped up to speed, and when we hit stop, and the drive turned off the IGBTs, so the drive output went to 0, and the spindle was left to spin to a free stop. So it took about 15 seconds for the spindle to coast to a stop on its own. Now I'm assuming you're watching this video because you don't want to wait 15 seconds each time you stop the spindle. So let's do that again But this time, let's go back to parameter 0.22 and tell the drive to do a controlled ramp to stop. Now the drive is going to try and control the spindle's deceleration. Parameter 1.13 is the deceleration ramp time. Let's set that to a reasonable 6 seconds. The write was successful. Go back to the scope, start it, and start the spindle. Wait for it to ramp up, then hit stop. Adjust the display and measure the time it took to ramp down. Yep, right about 6 seconds. Exactly what we asked for. Let's do something crazy and ask the drive to ramp from 24,000 RPM all the way down to 0 in just 1 second. Write was successful. Go back to the scope and hit run. Start the spindle, ramp up to 24,000 RPM, and stop the spindle. Measure the ramp time. Took a lot longer than the 1 second we asked for, didn't it? Clearly, the drive wasn't able to overcome the spindle inertia during the 1 second we asked for. And what's the deal with these steps? Well, this is a special feature the GS20 series drives have that you won't find in inexpensive hobbyist drives. The GS20 drive is monitoring the DC bus voltage, and when the regen causes the DC bus to rise too high, it stops the deceleration ramp until the DC bus voltage comes back down. Then it starts ramping again until the DC bus voltage gets too high, when it lets the motor coast again. You get the idea. So basically, the GS20 is pumping the brakes, braking a little at a time to slow the spindle as fast as possible without generating an overvoltage fault. And we can actually see that. If I enable the DC bus trace and zoom in on that, yep, we can see the DC bus started to rise and then come back down during the coast portion of the step. If I zoom back out, you can kind of see that. It's too bad these two waveforms on such different scales. It makes it hard to see everything graphically at the same time. But you can see the numbers as I scroll the cursor across the waveform. Each time the DC bus voltage gets too high, the drive turns the IGBTs off to let the motor coast while the DC bus voltage comes back down. The overvoltage trip point threshold is in parameter 601, which defaults to 380 volts for this drive. If we go look at our scope trace and zoom back in on the DC bus, sure enough, when the DC bus approached 380 volts, the drive released the motor to coast on its own. If we disable this overvoltage stall prevention by setting parameter 601 to a 0, what happens? Write successful, go back to the scope, hit run. Start the spindle, ramp up, stop the spindle. And guess what? We got an overvoltage fault on both the drive display and over here on the GSoft2 screen. And the spindle is spinning freely. Why? Because the DC bus got too big, so the drive just shut the IGBTs down to protect itself. This is how most hobbyist drives handle overvoltage faults. They just shut everything down. I'll press the stop to reset the fault. Re-enable the overvoltage protection by setting this back to the default 380 volts. Okay, so bad things happen if we try to decelerate the spindle too fast because it raises the DC bus. Got it. Now I'll flip the switch I added to enable the braking resistor and rerun that 1 second deceleration test. Start the scope, start the spindle, ramp up, stop the spindle. Wow, look at that. It easily stopped the spindle in 1 second, and we can see when the DC bus got to this level, well below the 380 volt limit, it held steady because all the excess energy got rerouted to the braking resistor away from the DC bus. We can see how stable this DC bus was during this deceleration. Nice. Well, that's all you need to know about braking to get super fast deceleration times on a GS20 series drive. To summarize, the GS20 braking options are: you can always coast to a stop. You'll never get an overvoltage fault doing that because you're not trying to force the spindle to slow down, so there's no regen energy coming back into the drive, raising the DC bus. The bad news is, it takes a long time for the spindle to come to a stop. Ours took 15 seconds. You can have the drive automatically extend the ramp time to protect the drive by pumping the brakes. This gets you the fastest possible deceleration without getting an overvoltage fault or damaging the drive, and without spending any additional money on a braking resistor. It's a pretty good compromise, and again, you won't find that kind of feature in your typical hobbyist drive. And finally, you can add a braking resistor. This gives you the absolute fastest deceleration because it can dispose of large quantities of regen energy. But it costs money, maybe $30 to $50, and adds hardware to your system that you have to wire and mount someplace. But you can't beat it for performance. Just for fun, let's go totally crazy and set the decel ramp time to 0. Now we know we can't instantaneously stop a spindle, but let's see how the drive handles it with the braking resistor installed. Start the scope, enable the spindle, ramp up, and stop the spindle. Well, the drive tried to stop the spindle so fast, the spindle was still moving after the drive was done and was just left to free spin down the rest of the way. So even though the drive was fast enough to do it in theory and the DC bus was totally protected, real-world physics got in the way. The spindle motor hadn't quite finished spinning after the drive was done. Is there anything we can do about that? Actually, there is. It's called DC braking. It tells the drive that instead of fully releasing the motor after ramping down, it should apply a little DC current to hold the motor in place. This is a duration parameter. That is, how long should the drive hold the braking current? Well, that's a little silly for us, right? If we tell the motor to stop in 0 seconds, then add a few seconds of DC braking current, well, why not just set the deceleration to a few seconds and have full control over the spindle deceleration? DC braking is really intended for things like large industrial fans that might be rotating because of a draft in the room. DC braking is normally used to hold the fan still both before starting the drive to ramp up to speed and to hold the fan still after the drive is done ramping down. Now, could you play with that here? Sure, but it's not really worth the trouble, especially since we know we can easily ramp our spindle down in less than 1 second. If you do want to play with DC braking, these are the parameters to look at. So how aggressive can we be with a braking resistor? Instead of trying to ramp the spindle down instantaneously in 0 seconds, which is ridiculous, what about a 1/10 of a second deceleration? Not 0, but darn close. Any chance it can handle that? Well, let's try it. Right was successful. Bring up the scope, run. Start the spindle, ramp up, stop the spindle. Holy cow, it worked. And the DC bus was held at a reasonable level, so the drive is perfectly safe. The GS20 Series Drive just brought a 3 horsepower spindle to a complete controlled stop in a fraction of a second. That's amazing. Bottom line, the addition of a simple, inexpensive braking resistor to a GS20 drive gives you incredible control over your spindle. One final thought. How awesome is this free GSoft2 drive configuration and debug software? It makes changing and backing up parameters super easy, and look at all the different things you can monitor with the 4-channel scope function. And I love that virtual keypad. There's a whole lot more you can do with GSoft2, so I want to encourage you to click on the links in the description below to learn more about that. And don't forget, this drive has a built-in PLC, and its software and tutorial videos are also totally free. Learn how to use the GS20 drive's digital outputs to automatically control your dust collection system here.